Right, so welcome to the 17th lecture, I guess, on random processes. Last time, क्या किया हमने?
Moving average.
एक skip हो गया. आप नहीं थे? Did you skip the last lecture or what? Last lecture. So two things starting with E, yeah, estimation and ergodicity. Yeah, and we saw how they were related. Yeah. So what was an ergodic process? क्या requirement थी?
That depends on.
So what's a stationary process?
Time invariant process.
Stationary is whose?
Time invariant process.
In what sense? What is time invariant in there? Values तो change होती है ना उसकी. Yeah, so what is time invariant in a stationary process? It's that its statistics
Doesn't change.
is time invariant. Yes, that's a stationary process. And within that we saw a subclass which was ergodic processes. What was that?
So
It is, yeah.
जिस तरह ह्यूमन बिहेवियर हमारे पास नॉन एर्गोडिक होता है, चेंज होता रहता है. अगर
change तो चीजें खुद
Ensemble statistic or time statistic.
हाँ. So if the time statistics is the same as the ensemble statistics, right? That is what we call a ergodic process. So like the human behavior, we saw the ensemble could be, you see, thousands of families in Islamabad. That is ensemble, a group of random behaviors, and you see which, let's say this weekend, which picnic spot was most full in Islamabad. That would be ensemble behavior to see, okay, which spot is most popular. Yeah. Another would be to pick one family and follow them over several months to see which spots they go to, and then try to decide which is more popular. As we discussed, human behavior is non-ergodic, so you can also imagine that the two statistics you will get, let's say the most popular, average, whatever, will not be the same in this case, right? But in real processes, when we have phenomena coming from different machines, thermal phenomena, there are many situations where the time statistics is the same as the ensemble statistics. Why is that important for us? So why is that linked to estimation theory? Because then we can do away with the ensemble idea and just take long measurement of a process, right? And we say, okay, so we saw, I think this kind of sums it up nicely. Let's say one way to find the statistics of a process is to look at several of its realizations. Yeah, maybe at one point or a small set of points. Yes, you take that and you try to find its statistics. Yeah. Another way is to pick one of these realizations and let it go on for a long time. Yeah, and find that statistics. So the statistics you find here is the ensemble statistics. Yeah, and the statistics you find like this is the time statistics. Now, one thing is very obvious, that if this is a non-stationary process, that means the statistics is changing over time, then there is no possibility for the two to be same. So that tells us that ergodicity has to be within stationarity, right? So stationarity, and within that there is ergodicity. And why was that useful? In most situations that we come across, we don't have access to ensembles, we have access to data over long periods of time. So we want a justification. If I measure a process over a long period of time and take out the mean, the variance, the covariance, all the statistics, is that estimate justified or not, right? And For ergodic processes, that is justified, because in ergodic processes, what happens, as I said, all for one and one for all, if you remember, this is that in each realization, if it is long enough, the entire behavior is represented. Okay, so the entire behavior is represented in a, and we saw very specific examples of rolling a die. If you recall those, you have the notes, scan of the notes, you can see the figures again, but there you should have been able to connect already that there are situations where this will the ensemble, yeah, behavior of the ensemble will be reflected in behavior of any one of them if you take it long enough. We saw a rolling a die example, and then before that we saw another example of a random process where that was not the case, right? If you picked one of the realizations, you wouldn't they would not represent the whole family, yeah. So these are different ways of saying it. And then last time I said that we will try to then write it more precisely, and also talk about ergodicity in the mean and like that. So two laws that I just want to mention quickly that are related somehow here. One is weak law of large numbers. Weak law of large numbers. सुना है आपने? Law of large numbers सुना है ना? सेंट्रल लिमिट थ्योरम वगैरह और इस तरह की ना. एग्जैक्टली हम अभी उस तरफ नहीं जा रहे, सेंट्रल लिमिट थ्योरम बाद में आएगा, लेकिन वीक लॉ ऑफ लार्ज नंबर्स basically says that, so you can find it in Kobayashi, the other textbook we have, right? So if you have a sequence of random variables, let's say these, such that these are IID. Remember this?
Yes,
sir.
Yes. So what is their distribution? We don't know, but it's the same. Yeah, there's no restriction on how they are distributed, as long as each one has come from the same distribution and they are independent of each other. Okay, as long as that holds, then this thing, let's say and then we have an additional assumption. This is the first assumption. Second assumption is that they have a constant mean, well-defined constant mean. So for any xk, the mean is mu. Okay, so at least the mean is stationary. It's not time varying, because it's not mu k. It's just some constant mean here. And finite variance. So the variance, whatever each one of them has to be finite. Okay, then it can be let's first define the time mean of this guy. This is the true mean. Okay, how do we get it? True mean, you get the true mean by taking each possible value of xk and multiplying it with the probability of that value. That is what we call true, and the true is always ensemble. The way we started, true is the ensemble statistics. Okay, so true means by definition, or for us. The other one that is coming now is the time mean. Okay, let's say I don't have access to the ensembles, but what I do have is access to n samples of this random process. Okay, then what do we do normally? Do we do it like this or not? The average. यही करते हैं ना? There is a good reason behind it actually. The law of large numbers, weak and the strong. Okay, it's a very justified thing, because in the many situations that we work with, the reality is like that. That the random happenings are independent. If you are concentrating on a particular problem, they are most likely coming from a same distribution. They could come from distant distribution, then you will have more loose laws and more discussion, more advanced. But we just want to get the basic stuff here. So you see the difference between these two or not yet? This is ensemble mean, the true mean. Yes, and the way this expectation operator will work will be with the probabilities. If it is discrete summation x I k, this k has summation x k I and probability x k I and I over in whatever sample space that guy is supposed to have. If it is discrete, if it's continuous, just integral. This is E, the true mean. This is not that, is it? Yeah? What did you do? You took n samples of this thing and you summed them and divided them by n. Yes? And this is what in normal language you call the average. Yes? Or arithmetic mean. Yeah? For now, to emphasize that this is not the ensemble or the true mean, we will call it the time mean. Yes? So this is time mean and this is ensemble or true mean. So now things are set up. The law of large, weak law of large numbers says that if this setup is as it is, then probability that xn bar minus mu is greater or equal to epsilon equals 0 for any epsilon greater than 0, with the condition that limit n goes to infinity. Okay, what is it saying? Can you interpret?
It is saying that if time is increasing, if time is increasing,
is time increasing or the number of
The
samples
number
you are
of
using
samples, number of samples
Yeah.
increasing, then it will be always greater than the ensemble. Greater than.
ये नहीं कह रही
The difference is
पढ़े पढ़े
probability. The chances of their absolute difference for positive is always 0. The
for
chances-
any epsilon, so you can make it as small as you like.
Yes, sir.
आप पढ़ें इसको. The probability that the time mean is different from the true mean is infinitesimally small. Right? They're saying any epsilon, it will still be the probability that it happens to be greater than any epsilon is 0. In all probability,
It will
the
be
two will be very close to each other. Right? So what does that tell you? That actually tells you that for this kind of setup, which is actually very common in real life problems, this is a good idea, as long as what? I mean, taking the average instead of bothering about finding the sample space, finding the whole probabilities. Yeah, true mean, that's how you would find sample space, then the probabilities, then estimate the mean. Instead of that, you can come close to this true mean through the time mean, as long as you take what?
more number of random variables.
Large samples,
Yes,
large
samples.
reading from here. Yes. So this is the weak law of large numbers. Okay, and in a way, this gives this formulation that you have been using since long as averages. It gives it its power. So okay, and we often write this thing in short form as xn approaches mu in probability. Okay, it's not actually approaching mu. Okay, the probability is, so what's the problem with probability? That the probability is approaching 0. That means there is still chance that it will be different from, yeah,
0, yes.
no, this difference from mu, right? So this is the weak law of large numbers. I'm not proving it here. I'm not sure even if Kobayashi has added the proof, but you can check if you're interested. Here we just want to connect the idea of time statistics and ensemble statistics, right? So then comes the strong law of large numbers. So here the approach was in probability, yeah. There is another thing. So if it is the same setup and there is a time mean here, then the strong law of large numbers, it says that there are two definitions. One is to say that xn bar approaches mu in the mean square sense. So I will define what that means, mean square sense. The other one is saying that xn bar approaches mu almost surely.
Surely, yes.
Yeah, almost surely.
Yes.
Yeah, that the probability that xn is not mu is almost
Sure.
0. Yeah, so it is almost surely, this is probability 1, xn bar is equal to mu. Yeah, so what is the mean square sense? It is basically, so again this is the time average and this is the true or the ensemble average. And when we say mean square sense, basically we are talking about expected value of xn bar minus mu square equals 0, with the understanding that the sample size is very large. मीन स्क्वायर सुना है कभी, कहीं यूज किया होगा? एक लीस्ट स्क्वायर होता है,
मीन स्क्वायर डिस्प्लेसमेंट.
yeah, it's used in many mathematical formulations, in optimization theory also. Least squares एक होता है that deals with deterministic things,
Yes.
and its counterpart that deals with the probabilistic parts is mean square.
Mean square.
Yeah, so this is mean square. Where is the mean coming from? This one here. Yeah, mean square. So what is it saying? It is saying that the overall xn is approaching mu, right? This is, we will look at it later also. This thing is very powerful. It shows that the variance of the deviation from mu is small if it is 0, and its average value is also mu. Okay, we will come to that when we talk about estimation. Yeah, almost surely here is basically saying this thing, that probability xn bar minus mu is less than epsilon with the limit n goes to infinity equals 1 for any epsilon greater than 0. Okay. So we write the strong law of large numbers in two ways. Both are saying that overall the mean, the time mean is approaching the true, the ensemble mean. Okay, and this is the strong law of large numbers, and you can read more about these later if you like, but for now I want to bring this when we define. Let's see if we have here mean square. Yeah, some of it will come up. So coming back to ergodicity now, we defined ensemble, right? What is collection of a realization of random process? Yeah. What is ensemble statistics? The statistics you take from that ensemble. Yeah. So let's say you have, I will quickly do that, we've already discussed it previously, so I don't know, maybe pollen is back or something. Trees have their own time. कुछ दरख्तों का शुरू में होता है, 2-3 माह पहले बहुत मसला था, stuffiness ना. I have serious issues. मुझे inhaler भी लेना पड़ जाते हैं. Right. So let's say you have this random process going on, x5 and so on, and as we said, let's say the realizations of this random process, let's say it can have 3 values, this thing, and then sometimes it takes this value, sometimes it takes this value, sometimes it takes let's say, so it can take different kind of values, right? All that and all more of those. Yeah. So if you take the statistics like this, again this is the ensemble statistics. But what if you could allow this process to go on? Then of course you would no point making all the samples, all the ensemble to go on. What if you could make one of them, allow that to go on, let's say taking the different values from among the possible subset, let's say it just keeps on it. And if you do the statistics of this guy, yeah, that is your time statistics. So I'm just repeating that. Now ergodic is, we have already said, is that if the firstly the process has to be stationary. Yeah, if it is stationary, then along with that, if all ensemble stats are the same as all time stats, yeah, so that is strict ergodicity. That is all ensemble statistics equals all time statistics. There is a check for that. So let's see. Without proving the check, I will just write it here, we can discuss it. A random process is completely ergodic if any ensemble expectation. So you want to take the expectation
of the ensemble.
Okay, of the ensemble, but not just the ensemble, any function of the ensemble. Okay, T1 to TP. So you are finite number of these things. Okay, you want to take an expectation of this function. Those of you who are familiar with some sort of moment generating functions and those things will recognize that actually this thing can represent all the moments of a random variable. Yes, and actually you can write the distribution of a random variable as a sequence or a let's say superposition of the moments also. Yes, yeah, so that's why this is powerful. It looks very simple, but it covers everything. What they are saying is this is actually the idea of all stat. Okay, so it's saying if for any finite set here from the ensemble, any function on it, g, arbitrary function, the expected value this one can be consistently estimated. There is an if here, okay? If this can be consistently estimated from corresponding time average. Now what would a time average look like for this situation? We will define what is meant by consistent estimation. Okay, that is part of this module. When we go to actual estimation, we define what is a good estimator, what is a consistent estimator, all that. So for now, just think of it as something that is a word that loosely means very reliable. Okay, but exactly what mathematically we will write it later. For now, if this expected value of any function of these variables here can be represented by the time average. Now what would the time average look like for this scenario? It will say I don't have to solve this, what you would need, this is a function of these random variables. You will need the whole sample space of this, yes, and then you will need to put all the values of the sample space, multiply them with their probabilities, and that will be your true average. Instead, you say I don't have that. What I do have is a long collection of this thing. So let's see how that looks. I say I have so we have capital X, I guess, yes, X, T, actually is values, so we will put small x, T plus T1 to X, T plus TP, and I have n of these. Do you understand this one? What is this? You have n of these, so you have, instead of the true thing or that thing, you have what happens when you put, maybe it can start with 0 also, it's fine, doesn't it matter, but let's say what happens if you put t equal to 1, you have x, t1 plus 1 up to tp plus 1. Then when you put t equals 2, you have t plus 2 and tp plus 2. So you have this sequence, you have it over time. Yeah, so this whole thing, the TP values are measured once, then you continue measuring them, right? Repeat again. That is what this will show, right?
Yes.
N times. You do that. And then what you're going to do is take those TP slices, put them on top of each other, sum them up, right? Overall, if you want to apply the function, of course you will do that, yeah, but you will sum the whatever the function is coming out to be, you will sum them up, and this will give you the time equivalent of this guy.
Yes.
Okay, and we are saying strict ergodicity is ensured if, we're not saying this will always be the case, we're saying if the true expected value of a function of this random process can be consistently estimated from a time average. If that can happen, then the process is strictly ergodic, because it actually means that you can get any moment, estimate of any of the moments, and if you can get all moments of a random process, it's fully defined. Okay, because that is in the moments is the whole information of even statistic. yeah, statistics. Okay, so needless to say, we don't really use it very often. Okay, it looks easy, but to prove it in general is quite hard. So it says, okay, it says something, but strict ergodicity, just like strict stationarity, is an ideal theoretical nicety. Yeah, you like it. In some cases, you can go for this analytically and do very rigorous math and get it. But in most situations, what do we do then? Again, this same idea that we have been doing before. What is a representative of the full distribution of the?
Expectation and discrete.
Yeah, the first two moments.
Moments,
Yeah.
yes.
So this is in a way talking about all moments. Yeah. We restrict ourselves to first two moments, and then we say, okay, a random process can be ergodic in the mean. It can be ergodic in the variance. Usually we stay up to that. Okay, so I'm not sure if we go up to even, okay, I defined second order ergodic also. Okay, so here, just like for stationarity, we did what? White said stationarity. Here we will go in two steps. In stationarity, we just jumped in one step to both mean and variance, yeah, because it was not too hard. Stationarity for mean only meant that the mean doesn't change, so it wasn't a bit hard. But here, even ergodicity in the mean requires some calculations or analytical stuff. So, so we are still following that model, and we go from strict ergodicity to ergodic in the mean. Okay. So when you study random processes after this, you will probably come up, or you will see this thing as assumption. They will say, yeah, we are assuming that it is ergodic in the mean, or we are assuming, and then they will justify with some ideas. So it is also called linearly ergodic. Okay, so in some literature, the same thing will be written like this, and as you can guess, what is it in words? It is in words is that the time average, time mean is the same as the ensemble. Yeah, but let's write it out here. To how do you show that? Okay, so a wide sense stationary random process xt with ensemble mean, let's say I've written m here, so I will stick to that. It has an ensemble mean m, the true mean, yeah, m, and it doesn't change, yeah, because we are saying it's wide sense stationary. So if it has ensemble mean m, is ergodic in the mean if limit n goes to infinity. As the data size increases, the expected value of mn hat, I will define what is mn hat, minus m square equals 0, where, as you can guess, what is mn hat now? This is of course the true mean. This is the time mean. Yeah? So mn hat is 1 over n summation xt, t is 1 to n. This is the time average of the process. So this is the test for ergodicity. Before we have just been saying it, yeah. Now you have a test for ergodicity in the mean. What is the test? If you can show, and this is actually not too hard to show for many processes analytically, you can show that asymptotically the expected value of mn hat minus m square equals 0, meaning in the mean square sense the two are same.
Same, yes.
Yeah. That is a time average. Now people have also devised quicker checks for this.
So, in a long run, we can say they will be same as an approach to infinity. That kind of sense we are producing for a long run.
Okay, so it's always helpful to see it, yeah, in the long run, or you mean large enough?
Yeah.
Large enough.
Yeah. When you approach something, you often in the mean square sense, it's often saying that, let's say this is the troop M, okay, and your estimates, yeah, are in different, distributed over different values, but when you're approaching in the mean square, let's first try this one. There can be other distributions also, but what the mean square sense says is this. It says that firstly, the average of your estimates is the true mean. Okay, so these are your estimates. Their average is the true mean. We will see later, this is called unbiased estimate. Yeah. Secondly, this also encompasses another thing. It says that the variance around this guy is very small. So essentially it's saying that as n goes to infinity, what's happening? This thing is shrinking. Okay. Eventually it should, in the limiting case, it should be here. So you get the right answer every time. Okay. Here you get the right answer on average, but you're not too far away from. Now, if it had been that you mostly got the right answer, you didn't have too much variance, but you are off from the true mean. So your mean was different from, then you are biased, and that's not a good estimate. But anyway, when something is in the mean square sense, it approaches another thing. Just imagine this thing. The mean square sense covers both. We will see that later when we come to estimators. That the mean square sense covers both these things. If it is 0, it definitely says that the estimates have an average which is the same as the true average. That is, they are spread evenly around this guy. Yeah. Secondly, their spread is very small. Okay, that is what's happening. So now, as I said, people have also devised checks for this thing to even make this simpler. To you calculate it, this is one main definition for linear ergodicity, but we have other checks. So this is the check we often use in practice. How to check? There is a sufficient condition. Okay, which says that limit tau goes to infinity, Rx tau equals 0, with the assumption that Rx, the variance of the process, is finite. Otherwise you won't be able to find this limit. Yeah, that's the only issue. This is not critical because usually that holds. This is the real thing. This is a sufficient condition. If you want to check, is my random process ergodic in the mean or not? Okay. First take its covariance function. Remember, for wide sense stationary processes, you don't need two values. You only need the gap.
Yes, sir.
Yeah? That's why I'm using this function, because if you remember, ergodic is within wide sense, within stationary.
Yes,
so we are allowed that. Okay. Then you don't need to do this mean square test or anything. The definition, you just go, you find the covariance of that random process, and often it is rather easy to estimate. You find that covariance and you see, is the covariance function vanishing as the gap between the samples increases.
Yes.
So if this is a random process, what is this saying? It is saying that if there is a covariance between these two, as this gap increases, the covariance disappears.
Yes, sir.
Or the correlation between them disappears. Yeah, they become asymptotically uncorrelated. So this sample is uncorrelated with, more uncorrelated with this sample compared to this sample with this, and the sample even further away is even more uncorrelated with the whatever the first one was. Why does it make sense? Why is it like that? Why, can you guess, or just get some picture of why this test would show ergodicity in the mean at least, or just some ergodicity? What has this got to do with?
Linear ensemble सर जो ensemble averages होते हैं ना वो time averages बराबर होते हैं
So इसमें जब हमारे पास टाइम एक्सटेंड हो जाएगा तो हमारे पास मीन तकरीबन सबका सेम ही आने लग जाएगा.
Right. So overall we are saying that of course the mean we get from here would be the same as the mean we would have gotten if we, let's say, had taken a smaller chunk but many of the realizations. Right? Usse jo mean aata, the mean you get now is the same, because that's what we're saying, yeah, regarding in the mean. Essentially what this is saying is this: when two samples become uncorrelated, yeah, that means that the correlation between them becomes they become, let's say, more independent of each other, isn't it? Close to. Uncorrelated is like an easy weaker version of independence, yeah. So if they are uncorrelated, we are basically saying that they are slowly becoming independent of each other. They are not really correlated with each other. Yeah. So if you remember the law of large numbers, where did it start? What was the first assumption? IID. Yes, IID. So identical distribution is already covered by the thought that they are stationary. Yeah. And now this thing is making sure of independence in a roundabout way. Yeah, pure independence is dependent, can be shown only through probabilities, yeah, and that would again be hard. Yeah, so in this case it is saying that okay, the data becomes asymptotically uncorrelated, so that is the next best thing we can do from independence, and the law of large number gives us a hint that as the data has become uncorrelated, the remember the sample ensemble mean, no, the time mean was approaching the ensemble mean. Yeah, so we are trying to replicate that condition here. Okay, and this can be derived directly from the definition of the linear ergodicity that I wrote before, which was that the expected value of mn hat minus m square equals 0, limit n. If you solve that, you will actually come to this formula. Okay, so there is also another way to test this, which is called the necessary and sufficient condition. This says that limit n goes to infinity 1 over n tau equals 0 to n minus 1 r x tau equals 0. The n is here. Yeah. So this is sufficient, necessary and sufficient condition. What should Rx tau property of this sum be for this to hold, by the way? Can you say something about this thing? What should it be for this condition to hold?
Some of the time differences.
First you
mean
know.
of the time difference, covariance time difference है।
Yeah,
अगर हमारे पास covariance भी time difference भी बढ़ रहा है और हम covariance की average भी उनकी ले रहे हैं इतने time difference से, then हमारे पास zero पे
yeah. So mathematically, if you think mathematically, what should this be for the whole thing to be zero? Just first think purely mathematically.
ओनली से हमारे पास या तो बहुत स्मॉल वैल्यू और n बहुत बड़ा हो तब भी हमारा
n
इक्वल
तो
टू जीरो नहीं, सबको जीरो होना चाहिए फिर तो। अगर इक्वल्स टू लेक्चर लाना है तो सबको जीरो होना या फिर हमारे पास सर इस तरह होना चाहिए कि ऊपर वैल्यू स्मॉल होनी चाहिए, नीचे n हमारे पास ग्रेटर होना चाहिए, देन इट विल गो
है ना? n तो ग्रेट हो रहा है ना?
यस सर।
नहीं, ये तो हो रहा है। वो कंडीशन मीट, फिर इस पे क्या कंडीशन?
बहुत स्मॉल होना चाहिए सर।
स्मॉल होना चाहिए या n तो इन्फिनिटी पे जा रहा है ना? So what should be the condition? Finite होना चाहिए, right?
Yes sir.
As long as this is, you know, this guy is going to infinity.
Yes sir.
So as long as this is finite, which is small compared to infinity,
Yes.
any finite is small compared to infinity, so is not in basically the the sum of the covariances is
Finite.
finite.
Yes.
Yeah. So the covariance function is such that it is finite. Now this thing encloses this also in a way, because the only way you can have that is that if it is diminishing. Have you ever come across an increasing or constant series that is convergent? Infinite निकलती है ना?
Yes sir.
The only way series become convergent is क्या होता है? बड़ा yeah, the increment is decreasing really faster than the increments.
Yes.
Right? यही होता है ना in a way. So that is what's happening. It is actually saying the same thing. Okay, but this is saying this thing, or again both of them are leading to this law of large number things. Large of large number was talking about independence. Independence is hard to talk about. We talk about uncorrelated. Okay, so if you have sequence where a sample here and a sample, let's say, million of time units away are still correlated, okay, then the law of large number thing won't hold, and you cannot say that this is ergodic in the mean. Okay, here at least, if their correlation is vanishing with time, or even better, whatever their correlations are, the whole function, the correlations sometimes high, sometimes low,
Yes.
but the total sequence of correlation that you get has a finite sum, which essentially means that they must be diminishing really
Yes,
fast.
sir.
Yeah, vanishing. So right, so then of course we go to second order ergodic, or ergodic in variance, yeah, or covariance. So this is second order ergodic. So a wide sense stationary random process with ensemble covariance. So we have a wide sense stationary random process with ensemble covariance. Again, ensemble covariance means for us true covariance, yeah, R tau. That is the true covariance. Is ergodic in covariance, I won't write that here, is ergodic in covariance if, we guess, it's very similar to what you saw for the mean. Okay, what was there? Limit n goes to infinity, expected value of r n hat, we will define this time covariance, yeah, minus r tau, we have to have a square here, equals what? 0. Okay, where r n hat tau is the time estimate of the covariance, and you get it like this. You say, okay, I will take t equal to 1 to n minus tau xt minus m xt plus tau minus m. Yeah, that is fine. We need a limit, I guess. No, okay, we don't for this one. It's just the definition. Limit is over there. Yeah. Okay. So tau greater or equal to 0. This is the time covariance of the random. What's the true covariance, by the way? R tau. What's the formula? Yaad? Expected value of
x minus
covariance of x of s and x of t.
Yeah, so which is, okay, let's start with that. Covariance of
x of s and x of t.
In this case, x of t and x of t plus tau. Yes, that is the case, and that is expected value of xt minus m
yes sir.
times xt plus tau minus mean of that, but it's vice and stationary, so mean is same. No, zero. दोनों का same है ना. This was the true covariance. To solve this, you would need the sample space and the average, the probability of each of those, right? But instead, we replaced the E by the time average. यही हुआ ना बस, बाकी तो वही है ना? So it turned out to be a bit easier because we had already established that for expected value, you just have to replace by the sum and average, yeah, division of that. So yeah, there is some discussion that if m the mean is unknown, you could replace it by the time mean mn hat, okay, to test for second order stationarity, ergodicity. Okay, and yeah, the conditions for this are a bit more involved, so we will not go into that. You have something now, or should we continue? We could take a slightly longer lecture. वैसे original time अभी खत्म नहीं हुआ है. Okay. So now this whole thing, this whole discussion was in a way the theoretical underpinning, theoretical foundation, or let's say theoretical justification of what we are going to do next. Asal ye tha, yeah, this wasn't the goal. It was just establishing under what situations the idea of estimating statistics of random things by observing them for a long time, in what situations is it justified. That's where the ergodicity and all these discussions came in. Now, with that aside, assuming now that ergodicity holds, if it doesn't hold, then of course there is another branch to work with. But assuming that the ergodicity holds, how can we estimate the different statistics, or say different details of a random process? So the definitions of ergodicity have already given you some estimates. Remember, we saw the estimate of the mean. Yeah, that was the time average basically. Yeah. So we saw the estimate of the covariance. जो भी लिखा था formula. So in a way, it's already started. But for going into actual estimates, I would like to talk about the overall issue of estimation. As I said in the start, uh, we started with, let's say, PDFs and PMFs, etc. We replace these by their fixed values, the mean and variance and covariance thing, yeah. And then we are now saying there was random process in between, but in this sequence now we are saying we want to replace this by their estimators, which are going to be time estimators, with the understanding that we are talking about ergodic processes. So the whole idea of working with time estimates is justified. Okay, that is this is here. But the interesting thing that happened now, if you are talking about, let's say, random variable x, it was random, the true is fixed, but the estimate, being an estimate, can be wrong, a bit wrong, little bit wrong, whatever. It is again random. Okay, इसीलिए तो हम इनकी expected, we were talking about its expected values, remember that basically overall the expected value we were saying of mu, let's say x, what did we write, m hat, I think m hat minus m square was 0 or something like that, yeah, limit n goes to infinity. Why were we talking about expected values? Because some of then one of these is random, and we know this is not random, it is fixed hota hai. The estimate is actually random. Okay, so this guy is random. Then okay, randomness here, as I mentioned last time also. If your estimator is good, the randomness of the estimator will be much less than the randomness you expect in the actual process. वरना तो फिर useless हो गया. Right? So now a large variety of applications require us to estimate these things directly from the data without using the true formulas, which would be the ensemble thing. So it does away with the issue of finding the sample space. It does away with the issue of assigning PDF, PMF, CDF, all that. Sab kuch side mein. Just give me the data. Either assume or prove that it is ergodic. Okay, and we normally assume it's ergodic. Okay, and then I can give you estimates of these moments for based on the measured data. And as I said, a lot of what we do in random processes, handling random process, a lot of formulas, a lot of estimators, detectors, classifiers, they work with the first two moments. So if you have their estimate based on this, and if the estimate is good, then all those methods are available to you now. Write a classifier, write a hypothesis test, whatever you want to do. Most of them will be based on the first two moments. If you can get their good estimate from the observation, long enough observation, that's it, and that sets the whole field of time series analysis. Okay, and this whole neural network things, and I keep saying it, but it's important, so I repeat it. It's actually an offshoot of that whole idea. It's like further extension of that idea. So if you understand these things, you are also ready to start working with machine learning, neural networks. Of course, you'll have to read some basics there, but the concepts will start coming back to you. So now, as I said last time, let's say you want to plan a wedding party and you want to make an estimate. One of you says 7 billion, yeah. One says only 7 will come. You say maybe 100 will come. Which estimate is good? How do we decide? What properties should an estimate have so that we can call it a good estimate? Yeah. So that is one thing that we will try to answer today.
That will depend who is saying that, the weightage of that person who is saying, and if he's more experienced then will weight to his means कि हम उसके weighted average ले लेंगे और हर weight.
So that would come to putting more confidence in that thing, yeah. But that is confidence. But how do you tell if an estimator or an estimate is good? Yeah. So yeah, a good estimator should give more weight to more credible information. That is fine. Yeah. So let's see in general what is a good estimator. Okay, so we want to talk about the word good. Okay, so have any of you done archery, tir andazi ya dartboard to kiya hoge? Yeah. Okay, so let's say you are playing a game of darts, and you know there is this bullseye and the dartboard. So let's say one of you throws 10 darts, okay, and they land here. Is this a good marksman or not?
No.
No?
No.
In one sense, this person is good.
एक ही जगह पर
Consistent है. Like Afridi हमेशा पहले ओवर में out हो जाए. Very consistent. Yeah. So, but the problem is he's focused on the wrong spot. Maybe he should stand a bit to the left. थोड़ा सा वो adjust करेगा तो maybe he can just get it right. Yeah. So it seems that getting the same place or being able to throw at the same spot or close to the same spots all the time, it's good, but not good enough if you are actually far away from the target. Yeah. Okay. So I can say that this guy is very consistent but biased, isn't it?
Yes.
He has a bias towards the right. हमेशा इधर ही फेंकता है. Okay. So we call this low variance. Why is the variance low? Because their spread is rather low. They are always
Yes, sir.
yeah. So you know accuracy and precision. Love सुने हैं? What's the difference?
synonyms ही है
Accuracy and precision. So actually that is how they are related. One of them, I'll let you search it later, and you can see one of them means how consistent you are, okay, and the other means how close you are to the true value. Okay, so in our case also what we want to see is there is low variance but there is a high bias. Okay, let's say I tell you that there is an estimator or somebody throws darts who is unbiased. Okay, somebody throws another one of you throws 10 darts and that person is unbiased. Will that be a good marksman?
It will depend if it targets in
Yeah.
on the
So
bullseye.
let's say that guy throws 6 here and 6 here. On average, he got the target. Yeah? So unbiased हो गया. Bias is like on average, are you there or not? So it seems that this guy is unbiased. So कभी equal amounts to the right and equal amounts with equal probability to the left. So the guy is not biased, but still not a good estimator. So firstly, this is biased. This guy happens to be, because the overall, if you just check the probabilities, because 6 times here, 6 times here, and if the distance happens to be same, just showing, then it is basically completely unbiased. Yeah. So that is good, but the variance is very high. Imagine its mean is where? Here, and What was variance? Remember, degree of spread around the mean. Yeah. So here its mean is here, and the degree of spread around the mean is very small. Here, since its mean is not here, it's actually here, the degree of spread around the mean is pretty high. So this guy is high variance, not consistent. Biased but consistent, unbiased but non-consistent. And from here on we say unbiased and high variance. So then now you are able to tell who is a good marksman. क्या चाहिए? Now the third person comes in who is really good. क्या करेगा वो? कहाँ होंगे उसके darts?
सर्कल के अंदर।
Right.
बाइस्ड भी होगा हमारे पास,
Unbiased.
बाइस्ड भी होगा और हमारे पास लो कोवेरिएंट भी होगा.
Low variance, yeah. It will be unbiased. Yes. So if you reduce the bias and the variance at the same time, where do you get all of these? कहाँ जाएंगे इनको? There is only one spot they should all go close to. If you want to reduce bias and variance at the same time, you have to concentrate towards the target bullseye. Then you have one definition of a good estimator. What is it? What is a good estimator then?
Unbiased भी होगा और
low correlated,
Low variance and unbiased.
Estimator is
So this is not the only way of defining quality of an estimator, but this is the most commonly used and the starting point. And it makes perfect sense. This estimator, this guy is low variance and unbiased, and you can see that the only way you can achieve both of them together if you are close to the target most of the time.
टारगेट तो एक ही जगह पर हो रहे हैं, अनबाइस्ड मतलब कि वो भी हमारे पास वही केस था, अराउंड थे एक ही जगह पर, ये भी इसी तरह से.
Yeah, unbiased means that the mean of this, on average, the mean is the true value. Yeah, इनका mean जो है वो कहाँ है? This guy has a bias that he always throws to the right of the. This guy is unbiased because with equal probabilities he throws to the right and to the left with same amounts. Yeah. So if you want to reduce both of them together, then okay. Now we can just put this in mathematics. That's it. Yeah, and get the idea of a good estimator. So what is a good estimator? Let's see. Firstly, in estimation theory, we often call the point or the parameter to be estimated as theta. This is true parameter, general word. By parameter, it can be then anything, yeah. And then there is an estimate of it, which is often represented with a hat, theta hat. So, and sometimes we also write it as theta n hat to show how many samples this estimate is based on. Okay, sometimes we write like this, sometimes depending on what you want to emphasize. Right, so then let's define what would be an unbiased estimator mathematically.
True जो है estimator की
Formula लिखो है.
जब
मीन जीरो होना चाहिए हमारा.
Mean of the difference.
दोनों के डिफरेंस जीरो होने चाहिए सर, जो ट्रू है और एस्टिमेट.
Yeah, so expected value of theta hat
minus
will be equal to
थीटा.
theta. There are other ways of writing it, yeah, the way you're saying, because it is, you could write it like this, that is fine. यही कह रहे हैं ना, because this is fixed, this is random, so you could just separate basically because of linearity of the expected operator, you could just separate and still get that. But now what is it saying? The estimator is unbiased if its mean value on average it gets to the true value. Yeah, and we define bias B as the difference. If it doesn't reach the true value, yeah, what is the difference? If B happens to be 0, the only way possible is if this holds, right? So when B is 0, the estimator is
Good.
unbiased.
Unbiased. Yes.
Yeah. So this is the definition of bias. How can we define consistency? So the second one, this was for bias, should be unbiased. Second is consistency. For consistency, we say that
Limit
goes to infinity. I will bring n here also. Okay, first I want to write this. Then the variance of theta n hat, meaning the estimate based on n samples, equals 0.
0.
So as you take more on more data, the variance of your estimator that uses that huge set of data
Becomes
should be
0.
approaching 0. You will not get it exact. If you get it exactly 0, you're not really talking about random process, right?
Yes.
तो वो तो फिर एक ही जगह रहेगा, वो तो कांस्टेंट की होती है ना,
Yes.
variance 0. So there is something called asymptotically unbiased. So true bias is hard to achieve. Asymptotically unbiased is similar to this thing, which is saying that limit n goes to infinity, expected value of theta hat n equals theta. Here we didn't say how many samples you want to use. So it's very hard to get an estimator which will be biased for any set of values, 10 values, 100 values. But asymptotic unbiased is allowing you to say, okay, as the data set increases, your bias should approach 0. That means you should approach the true mean. Meaning what? That if I give you a large enough data, yes, if I give you a large enough data, then if this is the true value and you are spread around this value, let's say I want to draw this, if I give you a large enough data, your mean value should be the true value and this variance should approach 0, get thinner.
Central limit.
Yeah. So limit n goes to, this is consistency. As I said before, I will define exactly what consistency means. This is mathematically called consistent. This is called bias. This is called consistency. Consistency is that as the sample size increases, the variance of your estimator that uses that huge sample is 0. If there is an estimator, you give it 1,000,000 values and its variance is still not approaching 0. That is not a good estimator. It's asking you for so much data and still this thing is not zeroing in on the true value. It should try to approach the true value. Variance should become 0. Yeah. So that is this thing. Now, how do you estimate the mean of an ergodic process? We have already talked about that. So, mean of an ergodic process. Yeah. Now, if the process is ergodic, simply you say, okay, I will. So you have a process, random process, and you say either assume or already proved that it is ergodic, or at least ergodic in the mean. Then a good estimator of this guy of the true mean is basically what we already saw. Take these n of these n samples from here, t equals 1 to n, and basically average them. Yeah. So that is, now can you check this, is this estimate unbiased? Check कर सकते हैं quickly. अभी तो हमने सिर्फ लिख दिया ना, yeah, but is this estimate unbiased or not? ऐसे ला कोई नहीं किस एक पेन है मिल के कर ले बोर्ड पे आ जाए कर लेगा मिल के कर ले डिस्कस कर लेना जल्दी व्हाट्स योर गेस बाय द वे
सर लिमिट लेंगे और लिमिट 0
वेरिएंस लेने के लिए
what are we trying to find if this estimator is biased or not?
yes
Yeah, and I've already said that the process is
Ergodic.
ergodic.
और बॉडी को हमारे टाइम डिफरेंस होता है अगर ergodic है तो हमारे पास ensemble मीन और जो दूसरा मीन है वो हमारे पास सेम होगा
So the process is ergodic. Does it have a fixed mean?
ensemble means a fixed one
Yeah, overall it has a fixed mean.
Yeah,
Yeah,
it
because
has
it's
one,
ergodic is within stationary, no?
yes
So it has a mean m. Now, if you remember, in the general case, we said if the true value is theta and the estimator is theta n
yes.
hat, then the estimator is unbiased if
expectation hat is equal to theta
this is what you have to show, that is EMN hat equal to,
and
if it is that, then you got it. Yeah, so can you show that? Just take the expectation of both sides.
this
Yeah,
expectation of XD you can
expectation of XT
start from
हमारे पास ये ergodic है stationary है independent है सेम होगा
and
टाइम्स और सेम एक्सपेक्टेशन आएगी m को यस सर आगे m के इक्वल आएगा क्योंकि सर हम जब सम करेंगे तो सबकी एक्सपेक्टेशन m है हमारे पास तो वो n बाहर आ जाएगा n से डिवाइड हो जाएगा
Yes, sir.
m आ जाएगा
right.
यस सर
And there is no, we didn't put any requirement of independence, by the way. Okay, only stationary and ergodic. Ergodic includes stationarity, but at least in this we didn't put any requirement of independence, right? So as long as this is ergodic, yeah, the xt it is unbiased. Okay, is it consistent or not? What do you say? So what did we say about consistency?
the variance of m
So limit
limit
n goes to infinity,
yes sir
variance of mn hat should be
0
0.
yes sir.
So basically you have to find the variance of this guy.
Variance of limit equal to n plus 0
ये हो जाएगी सर चीज़
हो जाएगी
yes
जल्दी कर दिया आपने so this is in theorem 2.4 in your book. You can see the derivation step. I will go to the final thing, that is variance of mn hat. Actually you will find that it will come out to be something like close to this thing. Okay, basically we are saying that with the condition that if RT is convergent. This is one requirement we will come across when you try to find the variance here. This will be several terms, covariance of Mn star with Mn star, Mn that will make pairs, right? Lots of pairs, and if you try to apply this whole thing there, you will come up with the covariance. And what will happen is that if you will come across this thing, and it will show you, okay, if that is convergent, then it approximately becomes this, and then limit. What happens now when limit n goes to infinity to this thing? So t is some value equals
Yes.
0. Yeah, because this is
Finite and
convergent, meaning finite. Then as the size of the data goes high, finite divided by finite 0. So it can be shown actually that this estimator, this very simple estimator, is actually a good estimator in that sense. It's unbiased and it is consistent. Yeah. So and there are other ways of writing it. I will skip that. I will also just mention one last thing and then we end it. So covariance of, how do you estimate the covariance of random process? So this was, we already have now an estimator of the mean, which is actually the time mean जो आप use करते आ रहे हैं. It is both unbiased and consistent. Yeah. So what about estimating covariance? So there are two candidates. आपको वैसे याद है, कभी देखा आपने covariance का estimate? So remember I said this will replace the expected value thing with the summation average thing. Yeah. So this is xt minus m, the true mean, times xt plus tau minus m. Yeah. The true mean of the ergodic random process. Second candidate is Rn star tau is 1 over n, t is 1 to n minus tau, this is also n minus tau, x t minus m times xt plus tau minus m. What's the difference between two candidates? One says I want to estimate like this, the other says I want to estimate like this. What's the difference? In estimation theory, you will always come across multiple estimators. Okay, so then you will have to define what is good in your sense. Sometimes you will go for a biased estimator if it's computationally taking less time. Then in your case, you may say, okay, I can afford some bias, but for me a good estimator is which takes very little time to calculate.
It will depend on the problem, sir.
Yeah. But then there's a finite way of saying it. It has to be like robust, numerically, takes less time, consistent, unbiased. If it has all the properties, well and good. If it can't have all the properties at the same time, then you will have to decide which properties are more important to you, right? So अच्छा रिश्ता जो होता है वो एक जुमला तो नहीं होता, और तो लिखा होता है अखबारों में, नमाज 5 और 6 वक्त के नमाजी 15 साल में 100 रोजे क्या लिखा वो पढ़ के बंदा कहते हैं आप इबादत ही कर लें. वो भी है, right? So what's the difference here? The only difference is that this divides by n minus tau and this divides by n.
N.
Which one makes more sense?
The second
How
one.
many terms are these?
Is equals to
N
N
minus
minus
tau
tau,
terms.
yes sir.
So then shouldn't the division be by n minus tau?
Yes.
This
Yes.
seems to make more sense, right? जितने normally averages में यही नहीं करते हम, we
Yes,
do
sir.
that.
N divided by
But there is an interesting thing. One of them is biased,
the other
okay, and the other is unbiased, or at least asymptotically unbiased, and you may be a bit surprised that which one is biased. Let's say we check the biases. Yeah, okay, I'll let you check that. Okay, so it's in your book also. This is discussed in chapter what? All of this is
chapter number 2.
2. Yeah, so in the other book this is in different orders, so it's fine. Anyway, you can check which one is biased, and then you can also check their consistency. It's a bit involved, so I will not go into that. That's it for today, and next time we will come across some, or we will talk about some examples in estimation. Okay. So we will take some real function, like for example, you remember that random harmonic.
yes, sir.
So if you wanted to estimate the, let's say, amplitude of a random harmonic, or you wanted to estimate some other function, the variance or something of a random harmonic, what estimators you can use, and then we shall try to show when are those estimators biased, unbiased, when are they consistent or not. Okay, so those examples we will see inshallah next time, and then mostly we are done with this module. After that we will come to the Gaussian and Poisson process. Okay, we have covered processes before, but these two deserve separate discussion in detail. Okay, last time we just saw Poisson as a special case of something, yeah, but now we want to really develop the Gaussian and the Poisson processes. Okay, so that will be the main module that we do.